to Engineering with Sophia, the show where we take complex technical documents and really break them down into what you need to know. Our mission is to take a deep dive into the source material you provided and give you that ultimate shortcut to being well-informed. I'm Sophia.
And I'm James.
Today we are taking on, well, the very foundation of how the physical world operates thermally. We're moving beyond the simple concept of energy. We're focusing on how that energy actually moves. We're plunging into the fundamentals of heat transfer.
And this is such an essential pivot point for any engineer. I mean, most people think of thermal science as just thermodynamics, but that only gives you half the answer.
Right.
Thermodynamics tells us about the state of energy. It can define the maximum energy required for a change to happen.
Okay, so if I have a cup of coffee at, say, 90 degrees Celsius, thermodynamics can tell me exactly how many kilojoules of energy I have to remove to cool it down to 80 degrees.
It gives you the destination,
Yeah.
the end state.
But it tells me nothing about time.
Absolutely nothing, and that's the key. Ask yourself, how long does that process take? Does it take 5 seconds, 5 minutes, 5 hours?
And that's where heat transfer comes in.
That is the domain of heat transfer. We shift the focus entirely from the quantity, which we call Q, to the rate of transfer.
Q dot.
Exactly. Heat transfer per unit time.
And as we move into design, that distinction, the rate, is everything. I mean, if I'm designing a power plant, I need to know how fast my steam condenses.
Right.
If I'm designing a new microchip, I need to know how fast I can pull heat away from the silicon. If I ignore the rate, I ignore time, and I guarantee that's an engineering failure just waiting to happen.
Oh, absolutely. It's the difference between a successful design and, like you said, a pile of melted plastic.
Yeah.
Knowing the amount of energy is useful, but the rate of energy transfer is the determining factor in, well, in almost all engineering applications. From sizing a simple home heater to designing the insulation for a spacecraft. It governs efficiency, safety, and longevity.
So before we jump into the 3 specific mechanisms that govern that rate, what is the single, absolute, non-negotiable requirement for heat transfer to even happen?
You must have a potential difference, specifically a temperature difference.
It's like gravity for heat.
That's a perfect way to put it. Energy always flows downhill. It travels from the high temperature medium to the low temperature medium. It's entirely driven by that temperature gradient.
So if 2 objects are at the same temperature,
You've achieved thermal equilibrium. The net rate of heat transfer is 0. We're only concerned with processes where that flow is actually occurring.
okay, let's unpack this historical context a bit, because the way scientists first thought about heat is just fascinating. It's completely wrong, but it has this strange legacy that persists even today.
It really does.
Before we understood heat as energy, there was this widely accepted view from the late 18th century, the caloric theory.
This was the main model for almost a century. It was largely formalized by the French chemist Antoine Lavoisier in 1789.
And the idea was what, exactly?
Heat was conceptualized as a substance, an actual thing, a massless, invisible, fluid-like element called caloric.
So if an object was hot, it just had a lot of this caloric fluid in it.
Exactly. And the cooling process was just that fluid flowing out of the hot body and into the colder body.
I find it so interesting that this completely inaccurate model left such a profound mark on our language. We still use terms like saturated liquid or saturated vapor in thermodynamics.
And those terms came directly from the caloric concept.
That's right.
Really? Yeah, they pictured a substance as being saturated when it had absorbed as much of this caloric fluid as it could possibly hold. It's a literal analogy, like dissolving salt in water until it's saturated. It was a very powerful, very intuitive model for its time.
But I'm guessing the moment people started working with mechanical friction, the whole system just kind of fell apart.
It did. The caloric theory held that caloric could not be created or destroyed. It was conserved. But Benjamin Thompson, also known as Count Rumford, demonstrated a very public challenge to this in 1798.
What did he do?
He was overseeing the boring of cannon barrels in Munich, and he noticed that the mechanical work of the drill continuously generated heat, seemingly without limit. As long as the boring continued, heat was produced. So, if heat was a conserved substance, where was it all coming from?
That must have been a huge theoretical crisis. I mean, if you can rub 2 sticks together indefinitely and keep generating heat, heat must be something else entirely. It's not a conserved substance.
Exactly. The definitive answer came in 1843 with these incredibly careful experiments done by James P. Joule.
And he's the Joule from the unit of energy.
The very same.
Yeah.
He used mechanical work like weights dropping to turn a paddle wheel in water, and he precisely measured the temperature increase. He established the mechanical equivalent of heat.
Proving that heat was what?
Just another manifestation of energy, specifically the random chaotic kinetic energy of atoms and molecules in motion.
And that, the kinetic theory, laid the foundation for the most critical principle in all of physics and engineering.
The conservation of energy. Precisely.
So now we understand that the total microscopic energy inside a system is its internal energy, which we call U.
Right, and we generally break this internal energy down into a few forms. The energy we can feel, the one that's proportional to temperature, that's sensible energy. It's the kinetic energy from random molecular vibration, rotation, and translation.
And then there's the energy that's used up not to change temperature, but to change the phase of a substance, to break or form molecular bonds, like boiling water into steam.
That's latent energy, or latent heat. That energy is sort of stored in the phase change itself.
And then there's chemical and nuclear energy, but for most heat transfer problems, we're really focused on sensible and latent.
For the vast majority of practical analysis, yes. And the umbrella principle governing all of this, thanks to Joule and others, is the first law of thermodynamics.
Energy cannot be created or destroyed, only changed in form.
And when we look at the rate form for engineering analysis, we state it as the rate of energy coming in minus the rate of energy going out equals a rate of energy change within the system. In heat transfer, we're often working with stationary systems, like a block of metal or a pipe. For these, the total energy change simplifies to just the internal energy change. We also often use a heat balance, treating things like electrical resistance or chemical reactions as simple internal heat generation, EGen.
Let's see what this looks like when we actually start calculating these rates. The source material gives us two really excellent examples that I think transition us perfectly from the amount Q to the rate Q dot.
Yeah, these are great. Our first case is a closed system, a fixed mass copper ball. We have a 10-centimeter diameter copper ball that we want to heat up from 100 degrees Celsius to 150 degrees Celsius.
And the process takes 30 minutes.
Right. So before we even worry about the 30 minutes, we need the thermodynamic amount, Q.
Okay, so we need the properties of copper. It's got a high density, around 800, 950 kilograms per cubic meter, and a relatively low specific heat, about 0.395 kilojoules per kilogram Kelvin.
If we run the volume and mass calculations for that 10-centimeter sphere, we find the mass is pretty substantial, a little under 4.7 kilograms.
Wow, for a ball that size.
Yeah, it's dense. So using the specific heat and that 50-degree temperature difference, the total heat transferred, Q, the total energy stored, is 92.6 kilojoules.
Okay, that's the amount. Now for the rate, which is the whole point of our deep dive. If that 92.6 kilojoules is transferred over 30 minutes, what does that rate look like?
Well, 30 minutes is 1,800 seconds. So dividing the total energy by the total time gives us the average rate, Q dot average, of 0.0514 kilojoules per second.
Or, to use the more common unit we hear every day, watts, that's 51.4 watts.
Precisely. That 51.4 watts is the average power that the heating element has to supply continuously for half an hour.
And without that heat transfer rate calculation, an engineer would just know they needed 92.6 kilojoules.
Right.
They wouldn't know if they needed a tiny battery or a massive industrial heater to achieve it in the time they want.
That makes the distinction crystal clear. That's exactly it.
Okay, so let's look at the second case, which involves fluid motion, a steady flow system. This is highly relevant to, buildings and infrastructure.
This is example 1.3 from our source material, and it deals with heat loss in home heating systems. We're analyzing hot air flowing through a 5-meter-long basement duct. The air goes in at 60 degrees Celsius and 5 meters per second.
And because it's losing heat to the cold basement air, it drops to 54 degrees Celsius by the time it gets to the end of the duct.
Right. And we need to figure out the rate at which that energy is being lost.
So since the air is flowing, we use the mass flow rate, m dot, as the critical parameter.
Exactly. We first need the air density at the inlet temperature, which is about 1.046 kilograms per cubic meter. Then, given the duct geometry, we can calculate the cross-sectional area.
And combining density, velocity, and area.
We find the mass flow rate, m dot, is approximately 0.26 kilograms of air passing through that duct every single second.
That's a significant amount of air movement. So once we have the mass flow rate, we calculate the rate of heat loss, Q dot loss, using the enthalpy change for the flowing fluid.
That's $Q to C76.2S. And since the temperature dropped by 6 degrees Celsius, the heat loss rate works out to about 1.58 kilojoules per second.
Again, translating to more user-friendly terms, that's 1.58 kilowatts.
Or 5,688 kilojoules per hour. That's the rate the air is just dumping heat into that cold basement space.
And this is where the engineering analysis goes directly into your pocketbook. That 5,688 kilojoules loss translates immediately to real-world cost.
Let's put some numbers to it. Let's say the homeowner's furnace is running at 80% efficiency, and natural gas costs are, say, $1.60 per therm.
And a therm is a huge unit of energy, right?
It is 105,500 kilojoules. So that energy loss rate is costing the homeowner about 10, almost 11 cents every single hour the furnace runs.
A little over 10 cents an hour doesn't sound like a lot.
It doesn't. But if we assume a typical heating season of 2,000 hours,
You're talking about an annual heat loss cost of approximately $216.
and that $216 is money that is just gone. It's lost purely because heat transfer was allowed to happen too quickly through that uninsulated ducting.
It just dramatically illustrates why the rate calculation is so crucial. It dictates not just the efficiency of the machine, but the cumulative expense over its entire operational life. That money is literally draining from the system into the unheated basement.
Right.
That $216 is a painful reminder of why we need to understand how to control QDOT.
So let's dive into the first fundamental mechanism of transfer, conduction. This is heat transfer by physical contact.
Conduction is the microscale mechanism of energy transfer. If we look at gases and liquids, it's energy transferred through the random elastic collisions and diffusion of molecules.
So a faster-moving, hotter molecule just bumps into a slower, cooler one and transfers some kinetic energy.
That's the gist of it. In solids, it's a bit more complex because the molecules are locked into a lattice structure. So there you have the lattice vibrations, the molecular movement within that fixed structure, plus the highly important energy transport carried by the free flow of electrons.
Especially in metals.
Especially in metals. That free electron flow is key to why metals are such good conductors. And it's why touching a metal object that's been in the freezer feels so much colder than touching a wooden block that's been right next to it.
Exactly. The metal is rapidly conducting the heat away from your hand.
The mathematical bedrock for this is Fourier's law of heat conduction.
Right. Fourier's law states that the conductive heat transfer rate, Q dot cond, is proportional to the area normal to the heat flow, A, and the negative temperature gradient, dTdx.
The negative sign is just a formality, right? It just means heat flows in the direction of the temperature drop.
Correct. But the real star of the show in that formula is the letter K, the thermal conductivity. This is the constant of proportionality, and it's where the material properties are all bundled up.
So K is the intrinsic measure of a material's ability to conduct heat.
Yes. It's measured as the rate of heat transfer per unit area, per unit thickness, and per unit temperature difference. And the range of values for K is just staggering. We're talking a factor of 10,000 difference between the best conductors like pure metals and the worst conductors like gases and vacuums.
Okay, let's quantify that spread. Water, a pretty standard liquid, has a K of around 0.6 watts per meter. Kelvin.
Right.
Iron, a common metal, is around 80. So metals are routinely over 100 times better at conduction than non-metallic liquids.
And that relationship between electrical conductivity and thermal conductivity is very strong because of that shared mechanism, the free movement of electrons.
So copper, for example, is excellent at both.
It is. Its K is around 400. But the absolute champion, the material with the highest known thermal conductivity at room temperature, is diamond. It hits an astronomical 2,300 watts per meter Kelvin.
Wow. I remember reading about that. That's why diamond is sometimes used as a heat spreader in high-end electronics.
Right, exactly. If you have a chip generating massive amounts of heat, you want to whisk that energy away as fast as physically possible, and diamond does it better than anything.
Okay, but here's where the material science gets truly counterintuitive, and this is where engineers have to be really careful. Alloys.
Yes, this is a great point.
I would assume if I mix two highly conductive metals, the resulting alloy would also be highly conductive. It just seems logical.
You would think so.
Yeah.
But consider constantan. It's an alloy of 55% copper and 45% nickel. Copper is a fantastic conductor. Nickel is decent.
Okay.
Yet constantan's thermal conductivity plummets to just 23 watts per meter Kelvin. Way lower than either of its components.
Wait, that's almost 10 times worse than pure nickel. Why would combining them make the material such a poor conductor?
It's the lattice disruption. When you mix the atoms of two different elements, you introduce impurities and structural defects into that nice, orderly, crystalline lattice. This chaos seriously impedes the free flow of electrons and disrupts the smooth vibration patterns that are needed for lattice conduction.
Ah, so the impurity atoms act like speed bumps, or maybe even roadblocks for the electrons and the vibrational energy waves.
Precisely. We actually use this feature sometimes. Constant tan is valued for its low electrical conductivity, making it ideal for things like resistance wires. But it shows how sensitive K is to atomic structure and purity. Generally, K is highest in ordered solids, drops significantly in liquids, and is lowest in gases.
Okay, so beyond just the raw ability to conduct heat, Fergo, we also need to talk about how quickly the temperature changes within the material over time.
Right.
And that leads us to thermal diffusivity, alpha.
Thermal diffusivity, denoted by alpha, is the critical factor for unsteady heat transfer problems, so when temperatures are changing over time. It's defined as the ratio of the heat conducted, first, to the heat stored in the material per unit volume, rho OCP. So alpha is K divided by first CPPF.
So it's a balance. How much heat is moving through the material versus how much of that heat the material just soaks up and holds on to?
That's a perfect way to put it. A large alpha means the material is excellent at transmitting heat quickly. It conducts well, and it doesn't have a high heat storage capacity. Silver, for example, has an alpha of about 149 times 10 to the minus 6 meters squared per second.
That sounds incredibly fast.
It is. Compare that to water. Water has a high heat storage capacity, a high CP, and only modest conductivity. So water's alpha is tiny, about 0.14 times 10 to the minus 6.
So silver diffuses heat 1,000 times faster than water.
1,000 times faster. The analogy of the spoon in the soup is perfect here. A silver spoon handle heats up instantly because its high He means it conducts heat away from the soup quickly, and its low rho CP means it doesn't need to absorb much energy before its own temperature rises dramatically.
Whereas a wooden spoon with a low K and higher storage capacity relative to its conduction takes forever to get hot.
And here's a fun fact illustrating the rho CP part. The thermal diffusivity of beef is virtually identical to that of water.
Which makes sense since meat is mostly water.
It does. And this is why cooking meat is inherently slow. It behaves thermally like a large mass of water, taking a long time for heat to diffuse to the center.
Okay, so conduction handles fixed solids. Now we move to the modes that deal with movement, beginning with convection, the primary mode for fluids.
Convection is, by definition, the heat transfer mode between a solid surface and the adjacent moving liquid or gas. It's actually a dual mechanism. First, there's microscopic conduction within the very thin layer of fluid that's right next to the solid surface. We call that a stagnant film.
Then
Second, there's the macroscopic or bulk movement of that fluid, which carries the heated or cooled parcels of fluid away.
So if I blow air over a hot plate, the air molecules right next to the plate get hot via conduction, and then the air current physically sweeps those hot molecules away and replaces them with cold ones. That whole process is convection.
Exactly, and we categorize it based on what's driving that bulk motion. Forced convection means we use external means, a fan, a pump, even the wind, to force the fluid to move.
The cooling fan in your computer or a hairdryer.
Perfect examples. And then there's natural or free convection. This is where the fluid motion is self-generated.
How does that happen?
It's all due to buoyancy forces. The fluid near the hot surface warms up, becomes less dense, and rises. Cooler, denser fluid sinks down to replace it, setting up a continuous circulating current that transfers heat.
And to quantify the rate of convection, we rely on Newton's law of cooling.
We do, which is metal displaced to H, X TS T, each TS T TSE. We have the surface area, AA's, the surface temperature, TS, and the bulk fluid temperature far away from the surface, T infinity.
But the critical term, the one that bundles up all the complexity of fluid dynamics, is that H.
That's the convection heat transfer coefficient. And we have to stress this. H is not a material property like thermal conductivity K. It is an empirical parameter.
Meaning it has to be measured or predicted through complex correlations.
Yes, because it depends on so many external factors. The geometry of the surface, the fluid's velocity, the fluid's thermodynamic properties, even whether the flow is smooth, which we call laminar, or chaotic, which we call turbulent.
And the range of H values is immense, reflecting that complexity.
Absolutely. I mean, look at the values here. Free convection of gases, like still air, is incredibly inefficient. The H might be 2 to 25 watts per meter squared Kelvin.
But then look at phase change processes, like boiling or condensation.
Right. There you have extremely rapid fluid movement and mixing because of the phase change, and the H values just explode. We're talking 2,500 all the way up to 100,000.
Wow.
That massive variability is why calculating H accurately is one of the biggest challenges in heat transfer design.
Okay, now we move to the final mode, and the one that truly stands apart from the other two, radiation.
Radiation is energy emitted by matter in the form of electromagnetic waves, or photons. It results from changes in the electronic configurations of atoms and molecules.
And the fundamental difference is that it requires absolutely no intervening medium.
None whatsoever. This is how the sun heats the Earth across the vacuum of space. And because it's electromagnetic energy, it transfers at the speed of light, the fastest mode possible.
The maximum rate of emission is defined by the Stefan-Boltzmann law, which applies to an idealized object, a black body.
And that law says the emission rate is proportional to the surface area and, critically, the fourth power of its absolute thermodynamic temperature, T's to the fourth.
And you have to use an absolute scale. We can't use Celsius here. It has to be Kelvin or Rankine.
It must be. And that fourth power term is incredibly powerful. Even small increases in absolute temperature lead to a massive jump in the rate of heat radiation.
So if you double the absolute temperature, you don't just double the radiation rate.
You increase it by a factor of 16, 2 to the fourth power. This is why furnaces glow bright red or white. They are radiating energy so rapidly.
And for real-world surfaces, we adjust the blackbody law using a property called emissivity, epsilon.
Right. Emissivity, epsilon dog, ranges from 0 for a perfect non-emitter, like a highly reflective surface, to 1 for a perfect emitter, a black body.
So a piece of polished aluminum foil might have an emissivity as low as 0.07. It radiates heat poorly.
Whereas something dark and dull, like human skin or a matte black paint, can have an emissivity of 0.95 or even higher. They're near-perfect emitters and absorbers. So the equation for a real surface becomes Dopian epsilon sigma, as TS42.
And related to emission is absorptivity, alpha, the fraction of incoming radiation that the surface absorbs.
And thanks to Kirchhoff's law, we generally assume that emissivity equals absorptivity. If a surface is good at radiating heat, it's also good at absorbing it.
So the net heat transfer by radiation is always the difference between what the surface emits and what it absorbs from its surroundings.
Exactly. So we end up with that final equation. Whole red, epsilon sigma, ACS4T SUR 4.
It's probably important to clarify how these modes interact.
It is. An opaque, solid surface can experience conduction internally, and at the same time, it can experience convection and radiation externally to the environment.
But a single medium can't have both conduction and convection, right?
Right, because convection is defined as the combined effect of conduction and fluid motion. And a vacuum, of course, can only support radiation.
And since most real-world problems involve a solid surface losing heat to its surrounding air and surrounding walls, that's convection and radiation happening at the same time. Engineers often combine the external effects for simplicity.
That's the utility of the combined heat transfer coefficient, H combined. It just lumps the empirical extra for convection and an effective linearized radiation coefficient into one single term. It simplifies complex surface heat loss calculations.
Okay, now that we have the three modes defined, conduction, convection, and radiation, let's see how engineers exploit or battle these processes in real-world design, starting with the ultimate battle, super insulation.
This is a fantastic illustration from the sources, example 111. It compares heat transfer between two parallel plates 1 centimeter apart. One is hot, 300 Kelvin, and one is cold, 200 Kelvin. The goal is to minimize the rate of heat transfer.
Okay, scenario 1. We put standard air in the gap. Air is a poor conductor, its K is low. We calculate the total heat transfer rate per square meter to be 588 watts. And crucially, we see that 219 watts is transferred by conduction through the air, but 369 watts is transferred by radiation between the two surfaces.
So even though air is a great insulator for conduction, the total transfer rate is actually dominated by radiation.
Right. Scenario 2. We create a vacuum in the gap. This eliminates conduction entirely.
So the heat transfer rate should drop.
It does. It drops to 369 watts, which is pure radiation. That reduction is significant, but it shows radiation is still the major player here.
Okay, now scenario 3. This is the most counterintuitive result.
Okay.
We fill the gap with urethane insulation. Urethane's thermal conductivity, its K, is actually higher than the air we used in scenario 1.
Wait, how can a material that conducts heat better than air result in less overall heat transfer? That makes no sense.
This is the engineering genius moment. The urethane is an opaque solid foam. It acts as a physical barrier that completely blocks the 369 watts of direct line-of-sight radiation we saw in the vacuum case. So, by replacing the transparent vacuum with a solid, albeit slightly more conductive, opaque material, you defeat the dominant mode of transfer in that scenario.
So the slight increase in conduction is more than compensated for by the total defeat of direct radiation between the plates. Incredible. And the total heat transfer rate plummets to 260 watts.
And finally, scenario 4. We use a high-tech superinsulation material which is engineered to have an apparent K of just 0.00002.
And the heat transfer rate drops to a minuscule zero point 0.2 watts. Compared to the original air gap, we've achieved a reduction factor of over 2,900.
And this leads us to the poster child of superinsulation, aerogel. People call it frozen smoke because of its translucent, ethereal appearance.
Aerogel is genuinely sci-fi material. It's created by removing the liquid from a wet gel through this process called supercritical extraction, which prevents the delicate nanostructure from collapsing.
And what you're left with is a material that is 90 to 99% air. It's structured as these tiny silica spheres, just 5 to 10 nanometers in size, forming these extremely sparse, chain-like connections. Its density is remarkably low, and its thermal conductivity can be as low as 0.01.
So how does this nanostructure defeat all three heat transfer modes at once?
It's engineering perfection. First, the incredibly sparse and tortuous path of the solid silica structure minimizes solid conduction. The heat just doesn't have much material to travel through.
Okay.
Second, those tiny pores, just nanometers across, are far too small to allow the bulk motion of air that's required for convection to occur. The air molecules are essentially locked in place.
And I'm guessing it blocks radiation, too.
It does. The silica itself is opaque to thermal radiation wavelengths, so it effectively blocks or scatters the radiation transmission.
It's a triple threat. The impact of this is huge.
It is. If you replace a standard 6mm glass window, which might lose about 133 watts under certain conditions, with a 6mm pane of aerogel, your heat loss drops to 1.3 watts.
That's a 100-fold reduction in Q dot.
A 100-fold reduction. The limiting factors, as you can imagine, are the high cost of that supercritical drying process and the fragility of the material itself. But its potential for deep-sea and space applications is immense.
Moving from efficiency to safety, the source material emphasizes the role of heat transfer analysis in prevention through design, or PTD.
This is a critical engineering ethics concept. It's about applying prevention efforts to eliminate hazards during the design phase itself, ensuring safety, health, and welfare are paramount.
And thermal hazards, particularly burns and fire risks, are a massive factor here. I mean, any temperature exposure above 43 degrees Celsius causes discomfort, but sustained contact above 70 degrees Celsius can cause instantaneous and severe damage.
And PTD mandates that we understand fire risks. This involves two key things. First, the flash point, the lowest temperature at which a liquid produces enough vapor to form an ignitable mixture with air.
So liquids with a flash point below 37.8 degrees Celsius are classified as flammable.
Right. And even more critical is the auto-ignition temperature, or AIT. That's the temperature at which a substance spontaneously ignites without any external spark or flame.
Let's apply PTD to a hot engine surface, from example 114. We have an engine compartment with hot oil that has an AIT of 250 degrees Celsius.
Yeah.
The interior engine parts are radiating a heat flux of 5 kilowatts per square meter to the outer casing surface. The surroundings are at 40 degrees Celsius. The question is, does the outer surface temperature, TO, exceed 250 degrees?
This is a perfect heat balance problem. The incoming heat flux, that 5,000 watts per square meter, has to equal the outgoing heat transfer rate.
Which consists of simultaneous convection and radiation to the environment.
Correct. We know the surface emissivity is 0.3 and the convection coefficient is 15. We just set up the balance. Incoming heat flux equals convection loss plus radiation loss, and we solve for the unknown surface temperature, TO.
And because the radiation term involves TO to the fourth, it's a bit complex.
It's an iterative calculation, but when we run it, we find that the outer surface temperature stabilizes at 552 Kelvin.
Which, in Celsius, is 279 degrees.
And that 279 degrees is well above the 250-degree auto-ignition temperature of the oil.
So the risk of spilled or splashed oil spontaneously igniting is real.
It is. The conclusion is that the current design, based on the rate of heat transfer, is unsafe and unacceptable under PTD principles.
The prevention through design solution is clear. You have to introduce insulation, a thermal barrier, to ensure that external surface temperature stays below that critical AIT threshold. If you fail to calculate the rate of heat transfer correctly, you create a fire hazard.
Absolutely.
We've talked about inanimate objects, engines, and ducts, but heat transfer is so central to the most complex system we ever engineer for, the human body and the environment we live in.
The human body is essentially a self-regulating machine, trying desperately to maintain a constant core temperature of 37 degrees Celsius. It does this by constantly performing chemical reactions, our metabolism, which converts the chemical energy in food into mechanical work and, crucially, heat.
The basal metabolic rate for an average person just resting is surprisingly high, about 84 watts.
It is. That's 84 joules per second, constantly being generated just to keep the lights on. And that rate scales drastically with activity. Heavy exercise can easily increase the metabolic heat generation rate tenfold.
So over 840 watts.
Easily. Think about that. Two people doing strenuous exercise in a small room could be generating more total heat than a standard 1 kilowatt resistance heater. Any HVAC system has to be engineered to account for that highly variable heat generation rate.
And engineering thermal comfort is all about achieving a heat balance between that metabolic heat we generate and the heat we lose to the environment.
Right, through convection, radiation, and evaporation.
Our sources identify three main environmental factors that dictate that balance. First, temperature. The optimal operative temperature range is 23 to 27 degrees Celsius for lightly clothed, sedentary people.
Second is relative humidity. This is critical because it directly impacts our body's primary defense against overheating, which is evaporative cooling. If the air is already saturated with moisture, sweat won't evaporate efficiently, and we feel much hotter. The desirable range is 30 to 70%.
And third is air motion, or draft. While some gentle air motion is useful, excessive velocity creates a chilling effect and is a major source of discomfort.
We can see the power of that T to the fourth radiation term when we look at thermal comfort. This is wonderfully illustrated by example 1 to 9. Why do we feel chilly in the dead of winter, even when the thermostat says the air is a comfortable 22 degrees Celsius?
My gut reaction is that the air temperature doesn't matter as much as the surfaces around me. In winter, the window glass and the exterior walls are significantly colder than the air itself.
Precisely. Let's quantify that heat transfer rate. We model a person with a skin temperature of 30 degrees Celsius and high emissivity, 0.95. In the winter scenario, even if the air is 22 degrees, the surrounding walls might average only 10 degrees Celsius.
And running the net radiation loss equation, that Ts to the fourth minus T sir to the fourth term, shows a radiation heat loss rate of approximately 152 watts.
Now compare that to a summer day. The air is still 22 degrees, but the interior wall temperatures are much warmer, say 25 degrees Celsius.
The calculated radiation loss rate plummets to about 40.9 watts.
That's nearly 4 times the heat loss rate in the winter scenario, even though the air temperature in the room was identical.
And that staggering difference in the rate of heat rejection, 152 watts versus 41 watts, is entirely explained by the T to the fourth radiation term. And that's the sole reason for that sensation of chill. Your body is just dumping massive amounts of heat to the cold surrounding walls.
And the convective heat gain from the 22-degree air just isn't enough to compensate.
The body, thankfully, has robust defense mechanisms. If we get too cold, what's the first line of defense?
Our bodies prioritize reducing the rate of heat loss. This happens via artery constriction, pulling blood flow away from the skin surface to decrease convective and conductive loss. If that fails, the body resorts to generating massive amounts of heat through involuntary muscle contractions, shivering.
Which can increase metabolic heat production up to 6 times the resting level.
It can. And in extreme heat, we just reverse the process. We increase blood flow to the skin to transfer heat outward. And if that's not enough, we initiate evaporative cooling via sweating. The human body is so efficient it can maintain its core temperature even in very hot, dry environments, as long as the humidity is low enough for the sweat to evaporate.
This all brings us to a final great comparison of engineered heat transfer, the difference between a conventional oven and a microwave oven.
Both cook food, but their heat transfer pathways couldn't be more different. The conventional oven relies on a slow, sequential process. First, the heating element slowly heats the air inside the oven. Second, that hot air transfers energy to the food surface, mostly via convection.
And third, that energy then has to travel slowly by conduction from the surface of the food inward to the core. This multi-step process really limits the overall rate of cooking.
The microwave, however, leapfrogs the two slowest steps. It uses electromagnetic radiation, not thermal radiation, but non-thermal EM waves. This radiation penetrates the food almost instantly and is absorbed by the internal water, fat, and sugar molecules.
So the energy transfer is volumetric and instantaneous, causing rapid internal molecular heating throughout the mass of the food.
Exactly. The slow external convection step is replaced by rapid internal radiation absorption. This means the microwave is transferring energy at full capacity the moment it is turned on, resulting in dramatically faster cooking times and higher energy efficiency. It is a fundamental redesign based on optimizing the rate of energy absorption.
We have covered a huge range today. We've moved from the conceptual basis of energy conservation to the microscopic physics of conduction, the fluid dynamics of convection, and the exponential power of radiation.
The core distinction we explored is fundamental to engineering. It's the shift from thermodynamics, which gives us the amount of heat required, to heat transfer, which gives us that crucial factor of time and rate, Q dot.
And that rate is dictated by three primary relationships: Fourier's law for conduction, Newton's law for convection, and the Stefan-Boltzmann law for radiation.
We saw how deeply material design impacts that rate, from the surprising anti-conductive properties of metal alloys to the nearly perfect insulation achieved by aerogel, which masters heat transfer on a nanometer scale by defeating all three modes simultaneously.
And we demonstrated that in any real-world design, all three modes interact. Whether we are analyzing safety using prevention through design principles to avoid exceeding auto-ignition temperature, or simply engineering a thermally comfortable room, the engineer has to predict the total rate of heat loss or gain accurately.
So what does this comprehensive understanding of heat transfer rate mean for you, the listener, in the long run?
Yeah.
Well, think about the most sensitive high-performance electronics in your life, your powerful computer processor, or the battery pack in an electric vehicle. These systems are constantly generating heat, often hundreds or thousands of watts. The difference between a functional product and catastrophic failure lies in the engineered cooling system's ability to pull that heat away at the required instantaneous rate. If the design engineer knew they needed to reject 100 kilojoules of energy, but ignored the fact that it needed to happen at a continuous rate of 200 watts, the component would instantly overheat and fail. The amount is a budget. The rate is the immediate constraint. Mastering the rate of heat transfer is literally the difference between a working system and a spectacular thermal meltdown.
That is a very powerful thought. The time factor changes everything. Thank you for joining us for this deep dive into the fundamentals of heat transfer.
Thank you.
And thank you, the listener, for tuning into Engineering with Sophia. We'll catch you on the next deep dive.